Alright, so in the previous class we saw that the most important result that we saw was, alright, theorem, that V of finite dimensional vector space over V over F. Alright, suppose V is a finite dimensional vector space V over V and T is a linear transformation from V to W. Did I write that V to W? Alright, so V is finite dimensional vector space W. W is another vector space over F. Alright, I am not saying that W is finite dimensional, I am just saying that V is finite dimensional. Alright, so that V has a basis. Fine. So let V1 to Vk be a basis of V over F. Then what we had was, then I can get any V, take any V belonging to capital V. I can write V as V1, V2, Vk basis vectors and some scalar which is alpha 1, alpha 2, alpha k. Is that okay? This is my V. Once I have this as my V, then this implies that T of V is nothing but T of V1, T of V2, T of Vk. Fine. But this alpha 1, alpha 2 to alpha k remains the same. There is no change there. This is what we had seen. Fine. What we had said was that the image of V is known as soon as we know the image of the basis vectors. So, these are the image of the basis vectors and therefore, it is just those alphas coming into play, nothing else. Fine. So, this is very important, you need to understand. So, what we are saying from here is that, so from here I want to imply that if I want to look at image of T, what is image of T? So, this stands for image of T. This is also called range of the function. So, range of T is all Tx such that x belongs to the V. Fine. So, therefore, if I look at this idea, what we see is that it is nothing but linear combination of these vectors. These alphas are there, they are just scalars. So, you are looking at linear combination of these. So, what we are seeing here is that it is linear combination of T of V1, T of V2, T of Vk. Is that okay? So, this is what is important. So, T of x I am looking at where x belongs to V. What we see here is that each of these T of x is known as soon as I know the images here of the basis vectors T V1, T V2, T Vk, and then I am just multiplying by certain scalars which are elements from. So, if I look at each one of them, they are elements from F, but overall they belong to F of k. Fine. If alpha is were real numbers, I am looking at r to the power k and I am just multiplying by that and nothing else. So, what we are saying is that image of T comes from just looking at the linear span of T V1, T V2, T Vk. So, this is the way that idea also is helpful to us. Now, as a corollary of this idea that T is known as soon as you know on the image. So, image of T is this, implies quite a lot of things. This will imply that even if W is infinite dimensional, implies even if W is infinite dimensional and even if this is finite dimensional, everything makes sense. So, whatever we have done is makes sense. We have done makes sense. The whole of this argument, W was not used at all, W was not used. This is what is important, nowhere W was used. Fine. And then we will come to a part, we will use this idea in finite dimensional, or if the dimension of W is greater than dimension of W or dimension of V, then you cannot have an onto function and things like that because of this part. All right. So we will come to that afterwards. So let us look at the first theorem, which is important here, theorem. Let T from Rn to R be a linear transformation. Then T of x is equal to, so this is a vector A transpose x for some A belonging to Rn. All right. So this is a vector, not a scalar quantity. Is that okay? Fine. So let us try to prove this. So what we are saying is that I am starting with Rn. I take a standard basis of Rn. So take a standard, or take the standard basis of Rn. So what was the standard basis? E1, E2, En. So I can write x as E1, E2, Ek, and if x is equal to say x1, x2, xk, then this is same as this times x1, x2, xk. There is no change there, fine, because this was a standard basis. And this will imply that T of x by definition that we have already seen is T of E1, T of E2, T of Ek times x1, x2, xk, fine. I want to get this A. So can you see that this is your A, all right. So define, all right, define T of E1, so define T of E1, T of E2, T of En, this vector as my vector A. If I do this, I get this as A transpose x itself. Is that okay? So you can see that direct idea gives you the answer, fine. So for example, if you want to look at an example, I define T of say x1, x2, x3, suppose I have got R3 here for me, and I am going from T from R3 to R. It means what? Each of them has to come only once in some sense, so it has to look like some, so if I look at this linear transformation, it will look like some 2x1 plus 3x2 minus 5x3, things like that. I cannot put any constant, no constant. Why no constant? Because linearity will be lost. This is what we had seen, that you cannot have linearity if you have a constant term for a linear transformation. We also cannot have a square, cube, a square root, sin x, cos x, so those things are not allowed. Only linear terms are allowed, fine, in linear transformation, and this is nothing but you are looking at 2, 3 minus 5 times x1, x2, x3, fine. So this is, so if you look at here in this example, what is T of E1? T of E1 means x1 is 1, all right, this means that you are looking at 1, 0, 0, so it is nothing but 2. Similarly, T of E2 is 3 and T of E3 is minus 5. So you can see that this theorem is valid, fine. So now let us look at, so for E, when I am looking at a standard basis, everything is nice, it is very easy to compute it. How do I compute when I do not have a standard basis, all right. So let me take an example to look at that part. Example, so suppose I want to construct, question is suppose we want to construct a linear transformation T from R2 to R2 such that T of 1, 1 is E and 2 and t of 1 minus 1 or t of say 2 1 is say 5 comma 4. I want to construct this. Suppose you want to construct this. Fine. How do you go about it? So, how do you go about it? Fine. So, the first thing we need to see is look at these two vectors, the vectors of the domain that I am talking of here. The vectors are 1 1 and 2 1. So, question is first question that you need to answer is this a linearly independent set? All right. The answer is yes. Fine. Since the answer is yes, I can do it. So, we can do it. We can do it. That is the first thing that you need to understand. Now, so I have to define, since I am defining a map from R2 to R2, I need to define it on a general vector x and y. So, what should be t of xy look like? What should this be? Fine. So, what we know is that x and y is any vector. I have to write it as this to be written as a linear combination of 1 1 and 2 1. So, if I want to write it as a linear combination of 1 1 and 2 1, I need to solve the system 1 1 2 1 times c alpha beta is equal to x y, where alpha beta are unknowns. Fine. I need to solve it, and which is same thing as saying that this implies that alpha beta is equal to 1 1 2 1 this inverse times x y. Fine. Is that okay? So, let us compute it what it is. So, the inverse of this is, I hope I am correct because I always do mistakes. So, determinant of this matrix is 1 minus 2, that is minus 1. So, I should get minus 1 coming into play. So, maybe minus 2 here or minus 1 here itself, and minus 2 I think. Let us 1 2 into 1 minus 1 is, so 1 multiplied by 2 1, so minus 2 multiplied by 2, so minus 2 and 2, this is 0, this is minus 1, the first one is fine. All right, the second one 1 1 into this will give me 1 minus 2 and minus 1 1, which will give me 0 here 1. Yeah, so this is okay, this is the inverse, no problem. So, this times x y, which is nothing but x minus 2y and minus x plus y. Fine. So, alpha is this. So, what we are saying is that this is equal to t times x y is nothing but alpha. So, alpha is, so it is alpha times 1 1 plus beta times 2 1. So, by definition of linear transformation, this is alpha times t of 1 1 plus beta times t of 2 1. Alpha here is x minus 2y times 1 1. Beta here is minus x plus y times t of 2 1. Sorry, what was t of 1 1? T of 1 1. So, it is, so I have to write t of 1 1. T of 1 1 is e comma 2 and t of 2 1 is 5 comma 4. So, I get this as x is coming with e. So, what are the coefficients of x? E minus 5 times x, y is 5 minus 2e, so plus 5 minus 2e times y. Then here again something. So, x is 2 minus 4, so minus 2x I hope. So, please check, I always do mistakes, all right. So, minus 4y and plus 4y is 0. Is that okay? So, plus 4y and minus 4y is 0. So, this is something again a matrix times xy. This is what I want you to see, that you can compute it. That is one thing. Fine. So, I would like to do it in a different way now. So, what I would like to, so that there is an understanding here. So, what exactly we have done, if you see, I wrote x y as alpha times the first vector, beta times the second vector, fine, and I am doing this. So, what I am doing is, if I look at this part, this is nothing but t of 1 1, t of 2 1, I am writing this, and then alpha beta, this is what I am writing here, fine. Just look at this part. I wrote this as a definition of linear transform, but basically what I have done is this, and that is what I have been emphasizing, that I want to look at images on the basis vectors. These were the basis vectors, all right. And what is alpha beta? Alpha beta is supposed to be this. So, I can expand it, I have done that part, but it is also this. So, what I am saying is that I have nothing but this is also equal to t of 1 1, t of 2 1, this is a matrix, and then I am multiplying by 1 1 2 1 inverse x y. So, I am doing this, fine, that is all I am doing here. I am writing alpha beta here with this, fine, and this, if I go here, if I write further here, I can think of this nicely, again this is 1 1 2 1 this. So, what I am doing is, all right, so let me just leave it as it is, I think that will be better. There is too congested here, fine. So, I want you to understand this. In this example, we could get it because of this being a linearly independent set. Let me look at another example before I come to the main theme, all right. Second theme is, so in example 2, want t from R2 to R2 such that t of 1 1 is 5 comma 4 and t of 2 2 is 10 comma 7. Fine, I want a linear transformation T with this property, all right. So, again as I said, first the question that you need to answer is, look at these domain vectors, are they linearly independent? So, if I look at 1 2 and 2 2, not linearly independent, and not only that, we are also able to say that 2 2 is 2 times 1 1. So, by definition of linear transformation, what we need is that t of t 2 2 2 should be equal to t times 2 of 1 1 should be equal to 2 times t of 1 1, this is what I am saying, which should be 2 times 5 4, which is 10 and 8. So, these two are not equal, fine. Since they are not equal, you cannot have a linear. So, we cannot have a linear transformation from R2 to R2 satisfying the given conditions. Is that okay? So, as I said, you have to first look at things and then proceed further. One more example, all right, or I will do some more examples so that we understand better. 3, all right. So, does there exist a linear transformation T from R3 to R2 such that T of 1 1 1 is 1 2, T of 1 2 3 is 4 3 and T of 2 2 2 or T of, let me add something different so that there is a, so 2 3 4 is equal to 7 8, all right. So, let us look at this part. Can I do such a thing? So, as I said, we need to look at the domain vectors. So, look at the domain vectors 1 1 1, 1 2 3, 2 3 4. Look at this set. Now, here I see that 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4. So, is linearly dependent. Not only that, we see that 2 3 4 is equal to 1 1 1 plus 1 2 3. Is that okay? So, this implies, all right, that T of 2 3 4 should be equal to T of 1 1 1 plus T of 1 2 3, which is same as 1 2 plus 4 3. So, it should be 5 5, all right, which is not equal to 7 8. So, such a linear transformation does not exist. Is that okay? So, this is what you have to understand, that whenever you want linear transformation, what we understand is that linear transformation is known as soon as we know it on the image. Fine. So, what image of what? The basis vectors, all right. So, I want to need to go to the basis vectors and see what is happening as such. Fine. That is very important for us, otherwise we will have a problem. So, at each stage we need to see the image on the basis and then proceed. So, here for example, now in example, if I forget about 7 8 and I say comma 5 comma 5, then what happens? So, does such a linear transformation exist? The answer is yes. Such a linear transformation exists, because if I look at these conditions are valid for me. I just check that I get 5 5 here, which is what it is, and therefore, such a linear transformation exists. So, but how do I define it? So, I know that on 1 1 1 1 2 3, these are two linearly independent vectors and they have the image, but R3 is defined using 3 vectors. It has basis consisting of 3 vectors. So, I can just take anything which is linearly independent of these two. Fine. For example, I can take my third vector. So, I can take the basis as basis of R3 as 1 1 1 1 2 3, all right, and I hope I think 1 0 0 is linearly independent, I think. Fine, because I cannot get 1 0 0, I can easily see. Fine. And therefore, I can take this and define T of 1 0 0 as whatever vector I think, whatever vector we want, because the main condition was these 3 conditions had to be valid. So, what we have done is we have verified that these 3 conditions are valid for us. So, I am not going to change the image of 1 1 1 because that is given to me. I cannot change the image of 1 2 3 because that is also given to me. So, what we do? We go to the basis, create one more vector to get the basis. Now, that vector can be sent to anything. We can send it to the vector 0 0 of R2, we can send it to 1 0, 0 2, e pi, whatever you can think of. This element can be mapped to whatever we want, and still we will get all the things that are required for us. Is that okay? So, this is what you have to understand. Fine. In the next class, we would like to look at, I will just state it so that you come prepared for it. So, there are these 2 definitions that I want you to recollect. Definition. One definition is image of T. So, T is a map from, say, any vector space V to any space W. Image of T is T of x, x belonging to V. Then there is null space of T, and if you remember in terms of matrix, I also wrote it as KER of T. We said it as kernel of T. This is all x belonging to V such that T of x was 0. So, this is all vectors of domain which is being sent to 0 vector, all right, everything which is being sent to 0, all right, and this is the image or the range of T. So, go back to your matrices, and or you can just prove it yourself that range of T and null space of T, they are spaces. So, vector subspaces, fine. Image of T is a subspace of W, null space of T is a subspace of V. So, we can talk of their dimensions. We can look at the rank nullity theorem that we had there. Rank of T plus nullity of T is equal to dimension of domain. So, here rank of T basically means dimension of range of T, nullity means dimension of null space of T is equal to dimension of V. So, we will be able to talk about it once this is a finite dimension, otherwise we cannot talk of things. So, in the next class we will look at this and try to proceed. Fine. Thank you.